big important principles, so on and so forth. So with this trig function, what I want to do is graph this, and I want to graph it over just a given domain. And that's the first big reminder that I want to talk about is since trig functions are periodic, a lot of times when we graph these, we just need to graph a period. And then once we graph that one period, we can figure out what is the period of the function, and then we can just keep repeating it over and over and over again. So that's why it's very common for these prompts just to say do this over a given domain. And like when we graph this, like I guess like we will include those values. So let's just do it over that one interval here. So with the trig values, like, just going through and say, okay, what are the x-intercepts going to be? What's nice about this is we're just wondering when is this going to equal 0? And this would equal 0. Remember, a fraction always equals 0 when we have 0 on top and when we have a number on the bottom. So like when I'm thinking about the unit circle and the interval, I'm just going to use some red to say like, okay, we'd start here in the negative pi over 2, and then we would continue to use these positive values. So you can see like we have like a full 2 pi. So when is cosine of x going to be 0? Well, the cosine of x would be 0 where on here at pi over 2 and negative pi over 2. Well, I should fix my notation. At x equals pi over 2 and negative pi over 2. But what happens at negative pi over 2, though? We should note that the denominator is undefined there, right? Because when we plug in the sign of negative pi over 2, right, the y value down here, that's just negative 1. So that does give us a denominator of 0. Which is why some people like to start by kind of just defining their domain first, which is fine. It doesn't matter as long as we consider when our function is undefined. So from here, I just know that my x-intercept is going to be at pi over 2 and 0. And then we also just figured out that we're going to have an undefined value, or in other words, a vertical asymptote at negative pi over 2. And then we could work on our y-intercept. So our y-intercept is just evaluating the function at 0. So it gives us the cosine of 0 over 1 plus the sine of 0, which is just 1 over 1, which is 1. So as an ordered pair, that's 0, 1. So we have our intercepts, and then we have a vertical asymptote. As we know about trig functions, they're periodic, so they don't have any like horizontal asymptotes that we have to worry about. So we're just going to list that as none. So then, again, when we're thinking about the vertical asymptotes, we already did that, but we're just setting that equal to 0. So if we didn't catch it, like how did we get that so fast? Well, that's when we were wondering when negative 1 was equal to the sine of x, and that's how we got that value. So we're always just checking all 4 of those important things. And with a periodic function, we don't need to think about end behavior, because what we'll just do is we'll just evaluate the function at these intervals, and then since it's periodic, we just repeat it. So there's not really end behavior since it's periodic. So we'll look at our first derivative. Now here we will have to use our quotient rule. So low times the derivative of the top. Derivative of cosine is the opposite of sine. Minus high times the derivative of the low. And 1 plus the sine of x, that constant goes to 0. The derivative of sine is cosine. All divided by low squared. And feel free if you want to simplify this on your own and just fast forward, that's cool. What I do want to, I'm just going to distribute to make some sense of this. Negative sine of x minus sine squared of x minus cosine squared of x all over 1 plus the sine of x squared. Well, we should recognize that Pythagorean there, right? Sine squared plus cosine squared is equal to 1. So if I multiply everything by its opposite and change the signs, negative sine squared minus cosine squared should be equal to negative 1. So then what we have is we just simplify the top. We already had the negative sine of x there. This quantity is replaced with negative 1. And then our denominator stays the same. And then I'm just going to factor out the negative on top because I want to see that 1 plus sine of x. And that helps us reduce the denominator then. So again, we're just making form based on the structure we see. So we can actually reduce the denominator to be just 1 plus the sine of x. So this is our first derivative, just kind of relabeling it over there. So if that first derivative, if we're wondering when is this going to equal 0, well, it's never going to equal 0. If I take a number and I'm splitting it up into a bunch of pieces, I'm never going to split that into or not have anything, right? Think about a candy bar. I know -1 doesn't make sense, but if 0 is not on top, if I start with 4 candy bars and I divide it by something, these candy bars are never going to disappear. I'm always going to have some portion of a candy bar. So in other words, if I take -1 and keep dividing it into smaller and smaller pieces, it's never going to be 0. The piece is just going to be super small. But then we could see when our first derivative is undefined. So it's going to be undefined when that denominator is 0. And we already talked about that before when 1 plus the sine of x was going to equal 0. That's going to happen at -pi/2. Now at -pi/2, we already said that was a vertical asymptote. So it's not necessarily like a point of, it's not going to be a critical point there because we know that we can't even use that value. It's not in our domain to begin with. So it's not going to be a possible point of extrema. So we're going to move on to our second derivative. Here again, we'll have to use our quotient rule. So well, actually, I think it's actually going to be a little more efficient for me to rewrite this, actually. I don't want to necessarily use that quotient rule, just because I can rewrite this as 1 plus the sine of x to the -1st power. And that, to me, is just a lot easier of a rule to use using that chain rule. So I can factor out that -1, and then if I start to use the chain rule, so I'll apply the power rule first. And -1 minus 1 turns into a -2, and then times the derivative of the inside. And the derivative of 1 plus sine, we already know, is just cosine of x. So then from there we can simplify, right? Those negatives will undo each other. And then that 1 plus cosine, that 1 plus sine with the negative exponent would be sent to the bottom. So we're wondering when this second derivative is going to equal 0. Well, that'll occur when the cosine of x is equal to 0, but then that denominator cannot be 0. And we've seen this before, right? This reminds us of the original function. The cosine of x is going to equal 0 at -pi/2, but that's not in our domain. That's a vertical asymptote. Or the cosine of x is going to equal 0, again, on the given domain, right here at pi/2. Then we also want to consider when our second derivative would be undefined. And that's going to happen when 1 plus the sine of x is equal to 0, because that's the only way to get 0 squared. And again, we're kind of seeing that value show up, -pi/2. That's not even in our domain. So at pi/2, we have a possible point of inflection, because that's where our second derivative was equal to 0. Now, as we summarize our work, I always like to put things on a number line. Now with this number line, since it's a defined interval, I'm going to put a dot on it. And then since it's a defined interval, -pi/2, and I guess I kind of missed one of our vertical asymptotes as well when I think about it originally. But it's fine. I always want to evaluate it at both ends of the interval, but I believe now that I think about it at 3pi/2, at 3pi/2, this equation here, right, -1 would equal, so 3pi/2 is another value where we have all these vertical asymptotes. So for all of these, that would have been true. But again, it's not in our domain to begin with. So I guess when we think about including those values, it's like maybe we don't need to include them because they're not, because they don't fit into the domain. And that's why I think this exercise would have given us that interval to work on, just because then we can find that we have an asymptote to an asymptote. So that'd be one full period. And again, that was just given to us to use that interval. So then from there, like the only thing that was really important to us is like we wanted to list the vertical asymptote, but then we also had a possible point of inflection right here at pi/2. So then in our table, it's a lot shorter and it's a lot easier for us. So right at this x value of negative pi over 2, our function was undefined. And then we realized that like that was the same for everything after that. So the first derivative was undefined there. The second derivative of x, that's that value that we saw. Everything was just simply undefined. So that's what we just do. There's just a vertical asymptote here. So then after that vertical asymptote, we have this interval of negative pi over 2 all the way to pi over 2, because that's that only number we listed as a point of inflection. And it's okay to just be using a calculator to help you to kind of evaluate some of these, just for the numbers if you need to, for the ease. I've already chosen some things to evaluate in like the first and the second derivative. They're not crazy to do. So like if on this interval, like choosing 0, you know, plugging into the first derivative 1 over 1 plus the sine of 0 or something, you know, similar, like doesn't matter. I already have a few values prepared just to ease the speed of the video. So on this interval, you should see that your first derivative is negative, and then your second derivative is positive. So we can conclude here is on this interval, our function is decreasing and it's concave up. Now we included pi over 2 in our table because we thought it was a possible point of inflection. So we can evaluate the function, and when you do, it comes out to be 0. You can evaluate the first derivative, and when you do, you should see that it's a negative value. And then we knew that it was on the list in the first place because it made the second derivative equal to 0. Now I'm not ready to see if there's a sign change in the second derivative yet. So I'm going to add another row to my table. So then we have our final interval of pi over 2 to that last point on the number line, 3 pi over 2. So on this interval, when you evaluate your first derivative, no matter what value you're choosing, maybe pi or something, I think we get a negative first derivative. So double check that. And then our second derivative would also be negative. So here we should see that it's decreasing and it's concave down. And now I can go back and see that in my second derivative, I found the point where it was equal to 0. And on one side of it was positive, and on the other side of it, it was negative. So we can conclude then that this was a point of inflection. And then the last part of our number line, this is when it was undefined again. And that starts to make sense as to why they gave us that interval to graph this on, vertical asymptote to vertical asymptote. So as we sketch this then, I'm going to go ahead and put one vertical asymptote here. So this is x equals negative pi over 2. I'll put another vertical asymptote here at pi over 2. And then that kind of nicely just splits the axes. So let's just put 0, or the y-axis, right in the middle. So we knew a few points to graph, right? We knew the y-intercept, right? We calculated the y-intercept to be 0, 1. And we calculated our x-intercept. Sorry, this value is 3 pi over 2. So this would be over here. So 0, 1 is our y-intercept. And then we calculated our x-intercept to be pi over 2. So I can label that at pi over 2, 0, our y-intercept. And then that was really all that was kind of going on from there. We already have our vertical asymptotes in, and the only thing that we saw was our point of inflection. So as we come decreasing from our vertical asymptote, we're decreasing and it's concave up until it hits that point of inflection at 0. I feel like I have an error now. 0, 0. Oh, sorry, our point of inflection is pi over 2, 0. Sorry, my bad. That's our point of inflection as well. This was reading the wrong table in my, or wrong line in my table. So our point of inflection. So in other words, I need to be decreasing and concave up all the way until I reach that point of inflection. And then after that, I need to be decreasing and concave down. That's my first attempt. It doesn't honestly look super amazing, so I might want to kind of redo some of it, and I'd recommend you do the same if that happens. So decreasing and concave up. I'm just kind of starting at the wrong spot. I feel like I need to come down a little bit steeper to kind of get that upward curve. All right. And I'll just kind of find the best fit. I think that's concave up. And then here I'm decreasing and concave down. And then after I do this, I always want to take a quick little peek to make sure that I'm not like outrageously wrong. And since we're just practicing, I think I have that prepared. So I think that looks pretty good.